Hello, ladies and gentlemen. We are going to get into our fifth section of trigonometry today, and this is going to be one that almost kind of stands on its own. We're going to go a little bit into what graphing trigonometric functions is like today, but then we're not really ever going to come back to it. You'll see this more in the later math classes. I just want to introduce you to the ideas that you might see. Oh, look who's joining us. Imagine that, Max. The sound that you might hear after I take her away is me plopping her onto the ground, in case you were wondering that. So, we're going to talk about trigonometric functions today and what their graphs look like. Since we've just finished talking about the unit circle, this is going to be very closely related. So the first thing that I want to do is talk about a few vocab words related to what the graphs of trigonometric functions look like. So trig functions are called periodic functions. Another name for that would be oscillating functions. That would be like oscillating. That's what the word oscillating looks like. And it means that they go up and down and up and down and up and down. If you look down your paper, you can see that that graph is going to go up and down and up and down and up and down. However, it does go in a pattern. Like, we could kind of isolate one section of the pattern. So if I said, all right, from here to here, that's one section of the pattern. It goes up and then down and then up. And if I continued, it would go up and then down and then up. So the period of a function, of any function that does this pattern where it repeats, the period is the horizontal cycle distance of a function. So the horizontal cycle distance of the function. So for example, if you look down here, this period of this function would be the distance on the x-axis. It starts at 0 and goes to, this is 6.28, that's the same as 2 pi. So it starts at 0 and goes to 2 pi. That means that this graph has a period of 2 pi. That cycle is 2 pi units long. All right? The amplitude of a function is the height of the waves of the function. So I'm going to call that the vertical height. The vertical height from the center, that's important, so from the center in a wave function, okay, because trig functions are not only periodic functions, they're wave functions, which is a special kind of periodic function. So if we look for amplitude, we're looking for how high or low the peaks of the wave go. But we're not measuring the distance between the highest peak and the lowest peak like this. We're measuring the distance between the peak and the middle, okay? In this case, the middle is the x-axis, but that won't always be the case. But we're measuring the distance between the peak and the middle. One way to do that would be to measure the distance between the tallest and lowest points and then divide it by 2, because then you would find that half distance. All right, and that's called the amplitude again. A phase shift, sometimes our functions can be phase shifted. That's a horizontal translation. So we can take our function, the base function, and we can shift it over slightly so that all the values are in a little bit of a different place. That's a phase shift. So it's a horizontal translation of a trig function. All right, and then vertical shift is just the other component of that. We can take this wave function and we could move it upwards on the axis. And that would be a vertical translation of a trigonometric function. So vertical translation of a trigonometric function. So what we're going to do today is mostly just look at the graphs and analyze them, figure out the period and amplitude, etc. for those graphs. We're also going to look at making graphs. So we're going to say, all right, how could we translate this base function graph and turn it into something else? And what would that graph look like? And what would be the characteristics of that graph function? So First of all, notice it says all graphs are presented in radians. So everything that we're going to be doing today is going to be in radians. Make sure your calculator is in radian mode if you're going to use your calculator as a tool today. So we're going to put our graphs in radian mode. Hello, Mac. Nice to see you again. And then we're going to look, and if you wanted to check your calculator, you'd see similar things as we have here. Now, what I want to do first, before we analyze, is I want to make this connection. Why is the graph looking the way it is? All right, and if you see, we have y equals sine x. This function, this graph represents the sine function. And in the sine function, we start at 0, and we go up to 1, down to 0. Notice that hits at pi, and then down to -1, and back up to 0. Why is that happening? So in order to notice why that's happening, we look at our unit circle, okay? Because the graph of a trigonometric function is basically the graph of the number of radians. So at 0 radians, our graph has a sine. Remember, sine is the y-coordinate. At 0 radians, our graph has a sine of 0. There is the coordinate point 0, 0 on your graph. At pi over 4 radians, our graph has a height, a sine of square root of 2 over 2. So if we went to pi over 4, which is like over here somewhere, then we see that it's going to be the square root of 2 over 2. At 90 degrees, or at pi over 2 radians, our graph has a sine of 1. So at pi over 2 radians, our graph has a sine of 1. At pi radians, our graph has a sine of 0 again. It went back down to 0, right? At 3 pi over 2 radians, our graph has a sine of -1. It went all the way down to -1, and then once we get back up to 0, it goes like that. So this graph is how many radians, what's the sine? How many radians, what's the sine? That's what we're measuring in our graph. All right, so when we look at these analyzing questions, we're going to say, what's the period? We already kind of talked about this. The period is from 0 to 2 pi. Makes sense, right? Because our unit circle goes from 0 to 2 pi without repeating. So this is going to go from 0 to 2 pi. So that means that the period itself is 2 pi units long. Right, here's the start of the period, here's the end of the period. So that piece where it doesn't repeat is going to be 2 pi. The amplitude going from the center line, in this case it's the x-axis, to the top of a wave. The amplitude, the highest this gets, is 1 away from the center. The lowest this gets is -1 away from the center. So the amplitude of this function is 1. There is no phase shift. This is a general form function. We didn't add or subtract anything. So there's no phase shift. It's right where it's supposed to be. There's no vertical shift. Again, there's nothing added or subtracted. It's right where it's supposed to be. The y-intercept of this function is 0. All right, and then the x-intercepts. And it's the x-intercepts within the interval 0 to 2 pi. So from 0 on the x-axis to 2 pi on the x-axis. Where are the x-intercepts? So we see one here at 0. We see another one at 1 pi or pi. And we see another one at 2 pi. So those are our x-intercepts. And we've analyzed the sine function. Let's move on to the cosine function. So here's the cosine function. Look at the difference between the sine and cosine functions. There's not too much difference except for this function starts at the top, okay? The cosine of 0 is 1. Check your unit circle to make sure. Start at 0 radians. The cosine is the x-coordinate. The cosine of 0 is 1. The cosine of pi over 4 is 0. Well, let's see that. Or sorry, pi over 2. The cosine of pi over 2 is 0. Then we have at 180 degrees, or at pi, we're at -1. At 3 pi over 2, we're at 0 again, and then we go back to 1. So look at this graph. We start at 1. At pi over 2, we're at 0. At pi radians, we're at -1. At 3 pi over 2, we're at 0. And then at 2 pi radians, we're back up to 1. And that's the same cycle. It'll start repeating again because it's like we're back to 0 degrees or 0 radians. So this is the cosine function. The period for cosine is the same as the period for sine, although if we look at it, it looks a little bit different. It doesn't go down then, or it doesn't go up then down then up. It goes down then up. But that's okay. The period is still 2 pi before it repeats. The amplitude is still 1. If we measure from 0, the middle, to the top of a wave, that's 1. There is no phase shift on a cosine function yet. There's nothing added or subtracted to make it move. There's nothing added or subtracted to make it move vertically. The y-intercept of this function is 1. And then the x-intercepts in 0 to pi. So from 0 to 2 pi, I see 2 places where it crosses the x-axis. I see this one right here. And if we think this is pi, then this has to be pi over 2. So pi over 2 is one of the x-intercepts. And remember, that makes sense because at pi over 2 radians, the cosine is 0. And then the other one here is going to be at 3 pi over 2 radians. Just like that. All right, so there's the sine and cosine functions. Go ahead and turn your paper over. We're going to look at the tangent function. Now, the tangent function is super weird. Look at this. This looks completely different than anything else. All right, but I promise it's using the same information. The same way that we could use the unit circle to show the sine and the cosine, we can use it to show the tangent. It gets a little bit trickier because in order to find tangent, we need to divide the y-coordinate by the x-coordinate, but we can do that. We could if we'd like. So let's look at this tangent function and analyze it. So let's see. The period of this function. Well, it keeps repeating this like swizzly up motion, right? Or if I look within this block, I have this little 2 swoopy symbols, and then I have another 2 swoopy symbols. So within every pi is when tangent repeats, okay? The other 2 trig functions have a period of 2 pi, but tangent has a period of just pi. So tangent will repeat its values, repeat its pattern every pi units. Okay, that's really important to know and to be able to distinguish that from sine and cosine. This is a function with asymptotes. Do you remember when we talked about asymptotes in class? So this function right here, if I were to draw like a dotted line like this is an asymptote, right? The function's going to get closer and closer and closer as I go higher and higher, but never get all the way there. We've got a spicy one on our hands today. Come here, kitten. And if we go down this way, the function's going to get closer and closer and closer and closer, but never all the way there. So this function doesn't actually have an amplitude because we can't measure the top of it. It's also not a wave function. It's a different kind of periodic function. So we're just going to write NA for amplitude. There's no amplitude in a tangent function. All right? Since this is the base function for tangent, there's no phase shift and there's no vertical shift. And then we look for the y-intercept and we see that the y-intercept here is 0. And x-intercepts in 0 to pi. So if I go from 0 to 2 pi, I see that there is an x-intercept at 0, an x-intercept at pi, and an x-intercept at 2 pi. So 0, pi, and 2 pi. So a couple of interesting things about the tangent function just to relate it back to the unit circle. The tangent of 0 is 0. And if I go over here and I say, all right, 0 degrees is going to be the y-coordinate divided by the x-coordinate, 0 divided by 1 is 0. The tangent of pi over 4, I know this is pi over 4 because this is pi and I'm just dividing it. Pi over 2, this would be pi over 4. The tangent of pi over 4 is 1. And if we look at the pi over 4 value, we have the square root of 2 divided by the square root of 2. That's going to be 1. Okay? The tangent of pi over 2, that's where our asymptote is. There is no tangent of pi over 2. And if I went over here and I did the tangent of pi over 2 and I did 1 divided by 0, you all know that that is undefined. even if some of you didn't put that on your homework when you should have. 1 divided by 0 is undefined. There's no tangent of 90 degrees because it's infinity, it's undefined, okay? And then we could continue here. The tangent of 3 pi over 4 is going to be the square root of 2 over 2 divided by negative square root of 2 over 2, which is going to then be negative 1. And if we check, the tangent of 3 pi over 4 is negative 1. And then we can go back up and we can just keep going and repeating that pattern. So what we want to do now is alter these trigonometry graphs. We want to say, what could we do to our base functions to change them? And so this is sort of our general form of a trig function. We've got all of our variables in here that do different things to our function. So the general form of any trig function is going to be y equals a, and then the trig function, this could be sine, cosine, or tangent, and then bx minus c plus d. So the a value is going to change the amplitude. These are kind of tiny blanks. Amplitude. So whatever a is going to be the height or the amplitude of your graph. The b is going to change the period of your graph. So whatever's in front of x here is going to change the period of your graph. Now remember, the standard period for sine and cosine is 2 pi. So the period in an altered function for sine and cosine will be 2 pi divided by the b value. The standard period for a tangent function is pi. So the standard, or the period for an altered tangent function is going to be pi over b, and we'll see that later. The c value here is going to change the phase shift. The c value is what's going to move your graph left or right. So phase shift. And I'm going to put here opposite. We've seen this phenomenon before, where if our phase shift is inside a set of parentheses, then it's going to move opposite. So if we have -4, we're going to move to the right 4. If we have +1, we're going to move to the left 1. So we're changing that to be the opposite movement. And then D is going to change the vertical shift of your graph. So vertical shift. So let's look at some examples here. It says analyze and draw the graph for y equals 4 sine of 2x minus 1. So let's think first about what this graph is going to look like based on this table of stuff. We have 4. What's that 4 going to do? That 4 is the amplitude. So the amplitude, instead of being 1, is going to be 4. This graph is going to have waves that are 4 times the height of the standard graph. Then we've got sine of 2x. That's a b value. That's going to change the period. So to change the period, we're going to say that this is going to be 2 pi over 2. 2 pi over the b value of 2. It's going to give us pi. So the period of this graph is going to be pi. Right? What that means is that this graph, instead of being a broad wave function, is going to be kind of closer together. It's going to be twice as squished together. Right? It has to complete its whole cycle in half the time. Then I see that I have a -1 outside the parentheses. That means that's a vertical shift of -1. We're going to move this graph down 1 from where it typically is. There's no c value, so the phase shift is 0. And then we'll figure out y-intercept and x-intercepts later. So let's start thinking about this. If our original sine function starts on 0, and we've vertically shifted it down, our new sine function is going to start on -1. Okay? If our sine function usually has x-intercepts at 0, pi, and 2 pi, if we're squishing that in half, then it's going to have x-intercepts at 0, pi, this is like pi right there, and then pi over 2. I gave you these numbers deliberately so that you'd have to think about the values that pi really means. So pi over 2 is just going to be right in between these two numbers. somewhere like that. And remember, this whole graph is shifted down 1. So instead of putting these dots on the x-axis, I had to move them down 1. So these are going to be sort of the inflection points. This is where it moves from going up to going down and going up again. And I could continue with these points if I wanted to, but I'm just going to draw one period of this graph. And that's all I need you to draw on your homework as well. So then we're going to say, all right, the amplitude, how high are the waves going to go? The amplitude is 4. So in between these two dots, the wave is going to go up 4. So let's count 4. We're going to say, all right, here's 1, 2, 3, 4. So up here, I'm going to make a dot roughly in the middle of these two. There is a dot. And then same thing is going to happen between these two dots. This is going to go down, and it's going to go down to an amplitude of 4. So I'm going to count 1, 2, 3, 4, and put a dot there. And now I'm going to connect my dots into this wave function. So remember, it's a wave. It's not just a zigzaggy line. So make sure you're trying to make it a little bit curvy. All right? If you can't do it totally, that's fine. All right, so this is what our graph is going to look like. And we can continue this if we want to, but if we don't want to, that's all right. You can be okay with just drawing one period of this graph. So we say, well, what's the y-intercept? We've shifted the function down 1, so our y-intercept is -1. And then I'm actually not going to have you do the x-intercept portion. This is something that you would have to calculate with a calculator because our intercepts are shifted. So they're not going to be nice numbers. So we're not going to worry about x-intercepts, and you won't have to on your homework either. All right, here's another graph that we want to look at. Analyze and draw the graph for y equals -2 tangent of x plus 3. So we have an a value, and our a value is -2. All right, so in this case, remember that this graph doesn't have an amplitude because it's a graph of tangent. So this -2 isn't going to be the top point of a wave, but I'm going to put here stretch because that -2 still does something to this graph. It stretches it. So now, where this graph had a point here, the new graph would have that same point up above. It's going to be a skinnier function than this one. It's not going to go so curved over in the middle. So it's a stretch of -2. Think about what the negative might end up doing to this graph. I want you to think about it before we write it. All right, and then I see a +3 at the end. That's a d value. That's a vertical shift of +3. All right, and I look and I don't have a b value, so my period is the same as it normally is for tangent, which is going to be a period of pi units. And my phase shift is nowhere to be found. I did not move left or right, so that's going to be 0. And so let's think about what this graph is going to look like. So remember that with the original tangent graph, I had asymptotes at pi/2. And then 3 pi/2. I had asymptotes in various places. So I'm going to come down here and maybe I'm going to put in some asymptotes first. My period is the same. So I know that at pi/2, here's pi, so pi/2, I'm going to have an asymptote, okay? So 3.14 is pi, so 1.6 something is pi/2. So let's put an asymptote there. Just like that. And then 3 pi/2 is going to be halfway between 3.14 and 6.28, so I'm just going to eyeball that one and put an asymptote there. Again, we're sketching, so it doesn't need to be perfect, okay? And then I know that in my original tangent, my y-intercept is 0, but I also know that I have a vertical shift of 3, so now my y-intercept is going to be up here at 3. All right, so I'll start that there. And now I have a stretch of -2. My original function goes up from 0, but if my stretch is negative, that flips it. Now instead of going up from 0, I'm going to go down from 0 towards my asymptote. So I'm going to start at 3, which is my new y-intercept, and I'm going to go down toward my asymptote, and I'm going to remind myself that I was a little bit whatchamacallit, a little bit more stretched because we have a stretch of -2. So I'm just going to go like, maybe that'll work. Right? And then I can kind of reflect it because I know it's going to be sort of symmetrical. So I'm going to try and reflect it this way. Just like that. It does not need to be perfect. We're sketching. Okay? Once again, right in the middle of our asymptote is where our value was at 0 before. So now it's where our value will be at 3. And then it's going to go down towards the asymptote. And it's going to go up away from the asymptote, just like that. So again, you can draw just a few of these in here. We want to draw at least one full period of them. So this is our graph for -2, tangent x plus 3. If you're not sure, make sure you use a graphing calculator. Check yourself so that you can see whether or not you have a similar function to what it should look like. Make sure your calculator is in radian mode because radian mode is going to be very important. Otherwise, none of these graphs will look right. Okay? We're going to say our y-intercept, which is 3, and then we're not going to do x-intercepts because our x-intercepts, once again, are weird numbers because we vertically shifted. So don't worry about those x-intercepts. All right? The two biggest takeaways that I want you to have from this section are, what are the general shapes and characteristics of each of the graphs of the 3 base trig functions? What do they look like? If I gave you a multiple choice question and I said, this is a graph of, is it sine, cosine, or tangent of x? Could you say that you for sure know that this is a graph of the cosine of x? Something like that. All right, and then the other thing I'd like you to know is, what do each of the letters do to our graph? So if we make a letter in the front here, what's going to happen to that graph? If you put a letter on the end, what's going to happen to that graph? What's going to change about the way it looks? So keep those things in mind when you're doing your homework, and you should be great. All right, get at me if you have any questions. See you later.